Alrighty, let's start it. So today we're going to continue our topic of virtual memory. And so last session we talked about the demand paging, how the virtual memory structure is and how it works. We talked about what is a page fault and how the operating system handles page faults, especially how it brings the pages on from storage to the memory. And we talked about the page replacement when we don't have enough available frames on memory, so we have to basically have a victim and offload that to storage and then load it another one, new one. And because for this page replacement, there are different algorithms. We talked about FIFO. We talked about optimal algorithm, which is also called Beladi's optimal algorithm. And then we talked about least recently used, and we figured out, okay, it's going to be a little bit expensive probably, and then we better go with approximations. So we also talked about MFU and LFU, least frequently used and most frequently used. They are actually in the lecture that I recorded. It is a little bit mentioned, but still, today we're going to talk about them because last session we didn't cover them. All right? So then make sure, I ask that you keep working on your argument passing as well as design document, which is due tomorrow. Yes, let's get into it. So today we're going to talk about, again, the approximations for LRU and counting algorithms, as well as what is thrashing, and do a couple of calculations and exercises on performance of demand paging. Okay, so this requires your attention. Again, this is something that I ask you to be aware, not to confuse with the performance of paging. There are a lot of similarities actually, but they're essentially, different metrics. All right. So this is an example. So we have a reference string for the pages, and now, assuming 4 memory frames, we want to implement the LRU 8-bit algorithm. This is one of the algorithms that might take some time. This is kind of round robin in your CPU scheduling. If it is a question in your homework or exam, make sure you spend time from the start and correct it, because if there's a mistake, it's just going to propagate itself, right? And then everything's going to just be a mess. So now, LRU 8-bit, we covered last session. It was when we have a byte that show a history of references to a page. Each time interval, we would shift it to the right, and then we insert a most recent, reference status bit from the left, right? So let me actually go and draw it on the blackboard. All right, you don't have to write this. It will be on the next slide, the solution. But I want you to actually know how it is solved. All right? So the reference string, I'm going to just, again, keep looking at here and one by one go read it. But it's just you need to know. For each frame, right? So we have frame 1. Let me just split it like that. And I'm probably not going to go all the way to the end, but all right. So this is going to be our reference string. Okay. The pages are going to come here, and then this is going to be frame 1. And for each frame, okay, I have been suggested to write a little bit better. I can't write larger just because, there's not enough space, but I try to write a little bit more clear. So, and number 4. So for each frame, we have a page, and we have also the reference bits. Okay, so it's kind of shortest job first, that you had to keep the burst time for each process at the same time. I don't want to refer to scheduling and refresh your memories, but no, it's because you have a history for each page and frame, right? And you have to keep that, and it's just easier to write it in order not to make any mistakes, right? So let's see. So initially we don't have any page in any of the frames. They're all free, and I'm going to just keep the lower portion of this as the reference bits, right? Because we don't have any page, we don't care about them, they're all going to be 0, okay? So once the first page comes, the first reference page is like 1. So we're referring to page number 1. It's not in the page table here, so we have to bring it in the memory. Do we have, replace any page? No, we have available free pages. Let's say, this is going to be our next victim, just because it's our first. So I'm going to bring page number 1 into this frame, and I'm going to set its reference page to 1 bit from the left. So if it's like 8-bit LRU, there are 8 bits, which are all 0, and then the first bit on the left is going to be 1. Again, I'm just saying it, I can't write larger than this, so if you're back in the class, try to, see where I'm pointing at. Again, you don't have to write anything. So, and then the rest of the pages is going to be the same, right? I'm just not going to update them. So the next reference page is 2. So when 2 comes, because one time interval has passed, page number 1 will be shifted to the right. So its reference bits will be 0, 1, 0, 0, 0, 0, 0, 0. Okay? And we already have a free page here, so there's no need actually to, replace that. So page 2 will be brought to this frame, and then the reference is also going to be updated. Again, because it's the first reference, so leftmost bit is going to be 1, followed by 7 zeros. All right? The rest is going to be the same. Okay? So the next time when 3 comes, this is going to be our free page, next free page. So this is going to come here. The same, but now 2 is shifted to the right, and it's going to be 0, 1, 0, 0, 0, 0, 0, 0. And then 2 is going to, the frame number 1 is going to shift like the 2 bits, like 1 bit from here to here, 1 bit from here. We're doing 1 at a time, so saying actually it's 2, it's a little bit misleading. Alright? So as you can see already, if you look at these numbers, the LRU bits, this shows the history, and clearly we can tell this number as a whole is larger than this, and that shows that this frame has been referenced more recently. And among these 3, for example, this is the oldest one. So it's clear. So again, at this point we don't need to, because we still have another frame. So where 4 comes, this goes here, 1, 0, 0, 0, 0, 0, 0, and then they're all going to just shift once. So this is going to be 0, 1. Be cautious when you do this, so not to make any mistake. It is likely, but... So one other thing that you can do, I'm going to... 0, 0, 0, 1, 0, 0, 0, 0. Okay? So next frame is going to be 4 again. So when 4 is referenced again, everything is going to be shifted once, right? We have it in the page table, so there's no need for replacement. But, so 1 is going to be here. It's going to be shifted one more time. So it's going to be like this. The 1 shifts to this place. 2 is going to look like this, just like 3 zeros, 1, and then again 4 zeros. In the case of 3, it's going to be 0, 0, 1, 0, and then 4 zeros in there. Now, the 4 is going to be shifted to the right, but because it's referenced, we're going to add 1 from the left side, not a 0, right? The page that is referenced is going to be adding a 1 in the left side, and then the rest of the bits is going to be the same, shifted to the right. So basically, you can think of it that this way. Every time we're updating the leftmost bit. If it's referenced, then it's going to be 0. If it's not referenced, it's going to be a 0. If it is referenced, whether it's like first time, second time, whatever, this bit is going to be like 1. Alright? So it's just going to let me go to the next as well. So for 3, because we have it in the page table, and you can also have your indicator right now, or at any point of time you can calculate it whenever you need it. So I don't have to keep track of this right now. Because right now I don't need it. The page is still available in my page table, so I take a look at it. Everything just gets shifted one more time to the right. 0, 0, 0, 0, 0, 1, 0, 0, 0. And obviously after some time, all of them, if it's not referenced, it's going to just be flushed. So 2 is going to be 0, 0, 0, 0, 1, and 3 zeros. 3 is reference, so I'm adding 1 here, but the rest of them should move to the right. So 0, 0, 1, 0, 0, 0, 0. And then the 4 is going to be just, again, pushing to the right with 0 to the left, 1, 1, 0, 0, 0, 0, 0. Okay? So now let's see. Oh, geez. So we also have 2 and a 1, and I'm just going to go quickly. So when 2 is referenced, this is going to be 1, 0, 0, 4 zeros, and then a 1. And then when 1 is referenced, it's going to like be 2 more zeros. Okay. I'm not writing this down anymore, and I'm not writing, I have to write this down because at the end I want to compare. Do I have to, or after that it's like, yeah, after that it's fine. So then 4 zeros. And so for 3, you're not referencing it, so it's just going to be shifted by 2, 0, 0, 1, 0, 0, 1, 0, 0, and then the 4 is going to be shifted again 2 times. I could have here. It's like this, right? Now why? What mistake? I missed just 1 bit. Yeah, I think that's right. So I just, like, it doesn't matter right now. Again, like, the solution will be on next slide. I just want to, like, show you how you pick the victim next time. So if you shift it twice, it will be 3 zeros, 1, 1. 1, 2, 3, 4. Okay. So at the end of the next one, so when 5 comes, you can see. So the 5 is not in the page table, so you need to bring it in. Do we have a free page? No. So we have to replace the page. Which page we're going to replace? The one that has been recently used with the looking at the bits. So if you look at the bits, so among these two, obviously this has been, this is larger than this, so I don't need to look at it. Among these, they have like, zeros. So this has been again, and then this, and then this. So this seems like a smaller number. This has been recently used. So I'm just going to pick this one as my victim, and the 5 is going to and the whole bits are going to be flushed, right? So we're not going to shift it anymore because it's the first time 5 has been referenced, so it's going to just be, refreshing. All right? So that's how you basically do it. And just like, again, make sure you pay attention. One way to do it, instead of like all these zeros and ones, if it makes simpler for you, you can use hex. So the first time you bring it, instead of like, 1 0 followed by 7 bits, 1 1 followed by 7 zeros, you can write like 80 in hex. And then every time you shift, you basically divide it by 4. Next time it's going to be 40. Next time it's going to be like 20. Next time it's going to be, but it's just like you have to like also follow. Remember how it like the leftmost bit of this nibble, flips to the other side. If it's like an odd number, then you have to add this one by 8. Again, not everyone is comfortable with that. If you are comfortable with hex numbers and nibbles, then you can obviously do that. But if not, it doesn't matter. Just like with the bits. Okay. So let's take a look at the solution here. And we can speak over the screen. So, as you can see, this is for the same string. It's going to start from here. It's going to be a little longer for the bits. So basically it starts from the first reference here all the way to here. And then it's going to continue from here. Just for convenience, I have basically copied this column all the way to here. Just so we can compare from this column to column rather than just looking every time like that, right? So just remember, this is the initial column. This is the same column as the last column here. So whenever you bring a page, you just replace it and you update the leftmost bit. Every time in interval, the pages that you don't reference, or even the one that you refer to, the rest of the bits will shift it to the right. If they're not referenced, there will be their leftmost bit is going to be 0. If they are referenced, that's going to be a 1, right? Does that make sense? All right. So, obviously you're going to spend some time on this, at home. Make sure you do, the same steps. You can come up with you can solve it to here at least, half of the string. All right. So there are 2 other algorithms. There are counting algorithms. Basically, instead of like, a bit that, you shift every time or something, it's going to be like, just counting. So you count every time a page is referenced, And obviously the implementation is not going to be, simple. If you want to do it in software, it's going to be very expensive and, it's not going to be effective. But at least, the idea of that is that, okay, if I'm just like, counting pages, references, then when I want to replace a page, I can pick the least frequently used. All right. So I'm going to take a look at and then, pick the one has the smallest number of references. And that's the idea is that hasn't referenced, so it's probably not useful. On the other hand, the same type, but the different argument is actually for most frequently used. And the idea is, okay, if a page is not, referenced too many times, maybe it's just brought new and it's not good, because if we just evict it, then we have to bring it back and, keep doing that. So, we have to pick the one that has been, most referenced. And, well, obviously that also has some issues, if it's a page that is actually being, continuously used, then that's not going to be a good pick, right? But these are just different ideas, and you should know them. All right? We're not going to go over any example, but the same table which is there, you can just, start working on them and make sure, you feel comfortable that any of these algorithms basically you can use. All right. So the next algorithm is the clock algorithm. This is a little bit tricky at first, but it's actually pretty simple. And it's an algorithm which is not recently used, or NRU, which is called a second chance. So it's kind of like the reference bit that we for least recently used, right? So if you remember, we had a reference bit, and we assigned a bit to each page, and if a page was referenced, then it was flipped to 1, and if it was not referenced, then the bit would be 0. Now, when we want to pick a replacement, we take a look at the pages. If there is a page that has a reference bit to 0, that means, okay, that page has not been referred to since when it was brought. So we're going to pick that. The issue was that among the one that have the reference bit zeros, we can't tell which one is older. Among the ones that have their reference bit to 1, so all of them have been referenced, we don't know which one has been most recent. Or what if every page has their reference bit to 1? How do we pick? So this is a good approximation that handles this by basically having all the pages logically in a circle, like a clock, right? And every time that we face a victim, we basically give it a second chance. So the first time the reference bit is 1, we're not gonna we're bringing it down to 0, so we give them a second chance. You have been referenced, but I'm going to give you some more time and see if you will be referenced again soon, right? And if the bit is 0, I'm just going to take it as a victim, all right? We'll see in an example, but the idea is, again, every page that we pick as a victim, if they have been referenced before, they get a second chance, right? We don't pick them. We let them be for the time being. We refresh their reference bit to 0 and basically tell them, okay, so I'm going to go around the clock and come back. If by that time you haven't been referenced, again, then you will be my victim, okay? But, next time whenever you come back to a page, if they are actually not referenced, then they will be a victim, okay? So that's why it's called a second chance. So that's why, it's also a clock, because it's a circular, like a logical circle, and then the pages are page number 1, page number 2, whatever, all the way. And then your clock hand is your victim selector. It's just start circling and then take a look at this page. Have you been referred to or not? If not, you're my victim. If you are, I'm going to refresh your reference bit, and I'm going to go around the clock. Next time, if you didn't use your chance to get a reference, then you'll be a victim. And it just keeps moving like that. So let's take a look at the example. So this is the logical circle. These are the pages, using for example, double linked list or something. Even I think a single linked list, it should be fine. It's just circular. And then the reference bit for each page is like that, 0, 0, 1, 1, 0. So if the clock arm is pointing to this, and now we need a replacement page, what we're going to do is that we're going to give it a second chance and turn it to 0. Move on to the next victim. This is still 1. So we're going to turn it to 0 and move on to the next victim. So this victim is actually 0. So from the last time that we crossed over this, they haven't been referenced. So they're a good victim. So we're going to replace them. Right? So that's the idea. So an example is this one. Again, the same table. And let's do a clock algorithm. I hope we can get enough time to solve it. Oh, it went all the way up. Actually, it might make sense to work on the same table, right? Or is it like too messy? I think it's too messy. All right. So instead of so when we bring strings 4, what is the next one? 4, 3, 2, 1. Ooh. 4, 3, 2, 1. I think by this time it doesn't matter. So first of all, we bring frame number 1, and with the reference bit here 1. Okay, and then we bring 2, and the arm, by the way, moves when you replace a page. So if initially my arm was here, when I bring the first page, then my arm is pointing at the next page. Right? So then this is obviously free, so I don't have to worry about that. So 2 comes here with the reference bit of 1, and then my arm is looking at the next one. So when I bring 3, then again the reference bit, the initialization of the reference bit is 0. I kind of got confused with the reference bit. Okay? Because they are just brought in, so you already are moving your arm past them. So, you should give them all the time for the next round to get referenced. So when you bring 4, again, you need to share it with 0. And your arm is now pointing at this one, right? So, here we have 1. By this time we have 2 and then 3. All of them have their reference bits to 0s. Okay, so far so good. Now, when 4 is referenced again, what you're going to do is that you're going to flip this reference bit to 1. Okay? All the other ones are just the same. Okay? Because it was referenced again, I'm going to flip this bit from 0 to 1. Next is going to be 3. Again, 3 is already in page table. It's just that the reference bit is 0. So what I'm going to do is, because it's referenced, I'm going to give it a 1. All the other things hasn't changed. I'm sorry if it's a terrible table. I hope you can follow this with your eyes. I can't. So the rest of them is just going to be the same, right? Next time 2 is referenced. Next time 1 is referenced. I'm just going to keep, looking at them and then see what's going to happen for the next round. So all of them are referenced once, and the arm is still pointing to 1. Okay? So that's the clock. Now, what happens for the next reference page? The next one is 5. So when 5 is, referenced, we don't have it in page table. So what are we going to do? We have to pick a victim. Who is our first candidate? It's this page. Is it a good victim or not? Well, they have been referenced since the last time we brought them in, all right? So let's give them a second chance. So instead, I'm going to flip this to 0 and then move on. So this also has a reference bit of 1, so that's not a good candidate. Maybe, I'm just going to give them again, flip this back to 0. In this example, because all of them are 0, all of them are 1, so this just happens, and all of them basically flip to 0, and then the arm comes back to the 1, and now, again, even though it's just the same interval, but the clock doesn't care. It just moves and then, looks at it. So right now, again, the victim is this one, and the page is 0, so the reference page hasn't been referenced, obviously, in this, one interval. So I'm just going to, remove that. So I'm going to replace this page and refresh this, and now the arm is picking at 2. Okay? So, but as an example, if, let's say, this had not happened, okay, if this had not happened, what would be the result? So this would be 0. I'm just giving another example because I don't want to go all the way to the whole string. So, but if this reference had not happened, the page reference bit for 3 would be 0. All of them are 1. So when 5 comes, the first candidate is 1, but it has the reference bit to 1. So we're going to flip it and then move forward. Is this a good candidate? No, it has been referenced. So I'm going to flip it to 0 and move on. Page 3 has not been referenced since we brought it, right? I mean, this is not there anymore, so since we brought it in, it hasn't been referenced. So this page, this reference page is reference bit is 0. So I'm going to actually pick that as a victim and replace that with 5. But now the 4 will stay wherever it was. Then the arm is now moving, looking at that. So next reference, whatever it comes, if it's in the page table, we're going to flip the 0 to 1. If it's not in the page, then we start like the clock algorithm. We take a look at the clock arm and then keep moving it until we face a 0. Flipping all the 1s to 0 as we move on. Okay? Yes? Let us consider what?
So we have undergraduate frame 2. So
here?
Yeah. So there is no frame 1.
Oh, here it's not there?
Yes.
Okay. Okay.
And we start from frame.
Okay. Let's do that.
Start from 1.
No. It just continues from where it left off. So when we brought the frame number 4, the page number 4 into frame number 4, right there we moved our arm to the next frame, which is circular, right? So right now the indicator is just pointing at this. I didn't write all of them, but it's just keep looking at it until we need to replace the page and run the clock algorithm. So by this time, this is 1, this is 0, this is also 0 because you said that this is not going to be referenced. So and when page number 2 is referenced, this is not going to change. This is going to flip to 1. I mean, it was already 1. No, it was 0 here. And then 3 is here with 0. And then 4 is here, right? So far, so good. We don't have any problem. We just flip this 0 bit to 1 because page number 2 was referenced. And the arm doesn't move. The arm only moves when we bring a page or we are looking for a victim and then we are flipping bits. Okay? So the arm is still looking at this. So now that the 5 is here, we're looking for a victim, right? Because we don't have the page table and we don't have a free page. So what we're going to do is, okay, we run the algorithm. The first candidate is this one, right? Because the arm is looking at this one. Okay. All right? So can I use this as a victim? Yes, because my arm is, picking this victim and it has not been referenced before. Right? So immediately I'm going to bring page 5 and the arm moves to the next one. Right? That's how it works. And that is why it's not a perfect algorithm. Right? Because it's an approximation. It tries to keep the overhead, minimum. And because of that, yes, maybe, page 1 was actually brought in, more recent than page 3. But we picked it as a victim. That's how the clock algorithm works. Yeah. Here? Yeah, that was our first example. You basically start flipping all of them to 0, and then you come back, and now you have a 0.
So you go to the 4 side.
Yeah. Yes?
Why does the arm move the 4 after the first 3?
This one?
Yeah.
Yeah? Why does it move?
Yeah, why is there 1 or 3?
It is. So every time that you bring a page, I didn't want to make it chaos. So, the arrow is initially looking at this one, which is available. Once you bring this in, this moves here. Once you bring this in, this starts looking at this one. Once you bring this in, it starts looking at the next one. Once you bring this in, it moves up. And so whenever you replace a page, or you flip its reference bit from 1 to 0, you move the arm. Yes?
So for 2, the one that is over to right? So since it's pointing to 1 and it gets access, does that mean we have to search for another one?
Well, when we reference 2, the 2 is in our page table, right?
No, like if after that you reference 1, then that means you have to search for another one.
Okay, you want to reference page number 1?
Yeah.
Where? Before this or after this? Okay, if the page reference, like you reference page number 1, then page number 1 is in our page table, and this reference only flips the reference bit to 1. Okay, the arm doesn't move now, because the arm only moves when we need a replacement, so, or we actually replace it. So this only does that, everything stays the same, and in this example now, when the 5 comes, we cannot pick 1 as an actual victim because it has a reference bit of 1. So what we're going to do is that we're going to flip its bit to 0 and move the arm down. Okay, basically we are not here yet. We are, still here, right? So can we use 2? No, because it has a page reference bit of 1. So we're going to give it a second chance. We're going to flip it to 0. And then the arm is going to look at the next victim. Is this a good victim? Yes, because this has a page reference of 0. So I'm going to replace this and then update my arm now to the next one. Yes?
After 2, if it was 2 again instead of 1, would the hand move down to 2?
No, by reference you don't move the arm.
Okay. But you would update the reference number 2.
The reference bit is only 0 or 1.
Okay.
Yeah.
So you would not update
No.
But if it was 0, you would update it.
Huh? If it was 0, you would update it to 1.
But still, the hand would move down.
Yeah. Okay? So, yes.
Is there a version of this where it uses a counter instead of just a bit?
Um,
Every reference to the counter increases, and then every time it loops back, it decreases.
So basically that increases the overhead. Technically you can use 2 bits, for example, instead of, that would be similar to that 8-bit one, right? So it's just like that in a different algorithm that works with 1 bit because it's simpler to implement, basically, right? You can implement 1-bit reference like that in hardware really easily, rather than a shift register for each page. Okay. All right. Yes. Let's see. So, by the way, for any of these algorithms, you have the number of page faults, page hits, and page replacements. Whenever you refer to a page which is in your page table, that's a page hit, right? And you don't have to, do any swapping or, paging in or whatever. That's called a page hit. If it is not in your page table, that's a page fault. Now, each page fault can be either a page replacement or just a page in. So if you have a free, frame, an available free spot in your memory that you can just bring your page, then the page fault doesn't end up to a replacement. Just like how we saw it in the first couple of, first few times. In this examples, we don't actually free any pages, so it only happens here. So, we have available pages, so we have a page fault, but we don't actually replace any page, okay? So we just bring them in. But at this point, we are replacing them because the replacement overhead is more. Because, for example, if they're dirty, we have to swap them out, right? So just know what these mean, okay? So, let's go to the performance of demand paging. This requires your attention. There are a couple of examples and exercises today we're going to cover. So, because of that, the algorithm of, the operating system keeping pages in the memory, there is always a page fault rate. So, there is, on average, there is a rate that, you have a page fault, right? It's always between 0 and 1. If it's 0, that means no page faults. The operating system is doing, so much, great at, having the frames ready on physical memory that there's no page fault. It just predicts basically what pages are going to be needed and then bring them in time. If it's page fault is 1, that's terrible, right? Every reference is just the OS is just doing random pages, right? It doesn't know what it's doing, whatever, right? So that's just the page fault ratio. Again, remember, these ratios, we also had one thing in the TLB. That was a hit ratio. It's basically the reverse, meaning, right? But that's how they, this is the metric. So, we consider that we have a memory access time, which is M. And then last session, we actually covered that this memory access time itself can be either a single access or two access if it's not in a TLB. So this memory access time can be also like an average. What is that? Has anyone any idea? Oh, construction. Yeah, I heard that somewhere. Okay. Okay. If you need me to speak a little bit louder, just let me know. I can do that. All right. So let's see. So just like think of this. When a page is accessed, right, if it's in the TLB, that means we know that, we don't have to take a look at the page table. The page table itself is cached, and we know what is, the page. Now, if we need to access the page table, now we want to access the physical memory, right? So the page table will tell if it is a valid page or an invalid page, right? Now, if it is a page hit, that means the page is in the physical memory. We read the frame, we access it, and that's it, right? So that's what the memory access time is. Now, if the page is not available in the physical memory, that's a page fault. So a page fault is now like an overhead. The time of a page miss is considered the page fault overhead, going to the interrupt, disabling interrupt, loading of the frame stack, whatever, right? And then, now we want to pick a victim to replace. We might need to swap it out and make some space. We might not. We might have available frames. That we don't know yet. But then we definitely need to bring a page from storage to the physical memory. And we need to access, we have an overhead of restarting that and accessing the memory again. Okay? So this is the time of a miss, and this is like extra. And this happens not all the time, only on the page faults. Okay? That's like how this is going to work. We're going to go over it one by one. Also, swapping out. Remember, I just said, the swapping out doesn't happen every time. It matters if you need to swap out. First of all, if the page is, you have to replace a page and you don't have enough free memory. Also, if you want to replace a page, last session we talked, if a page is not touched, you don't have to swap it out. You just drop it. If a page is dirty, it has been modified, then you have to swap it. This itself is a metric. You have an idea that, okay, on average, how many of the reference pages are dirty? Okay, this depends on the workload or whatever. This is just a metric that will be given to you. Okay, so this is a weighted average. So let's see how it works. Also, the effective access time, I actually will, it's like two approaches to compute. Like whatever you feel more comfortable, you can do that. So the idea is that the effective access time is that I have a hit rate, and every time I have a hit, I have an average hit time. Or I have a miss rate, and every time I miss, there is also an average miss time. So effective access time is going to look like that. It starts with that. So the hit rate, this is a page fault rate, so the hit is like 1 minus P. That's simple. The miss rate is P. So if we hit the page, what we only need is to access the memory, right? It doesn't, it's not that different. But if we miss a page, we need to access the memory eventually, but before that, we also go to the page fault, which is the overhead, the swapping out, the swapping in, and so forth. So, however, this line went to say something else, I guess. Maybe I copied it. Alright? So, there are overheads that we can ignore. For example, compared to the swap out and swap in time, the memory access time, restart time, even the fault overhead is not. Because you're dealing with like a hard drive, it's like milliseconds. But here you're dealing with like, microseconds. So you ignore those. And so the effective access time would be like 1 minus P memory access plus P only the swap in and swap out. And also this m and then m can will actually the negative pm and pm also cancel out. Again, they're also overhead anyways because p is much less than 1. So it basically translates into this. So for the effective access time is you have to access the memory, but at some ratio, which is your page fault, you also have an overhead, which this is it. Swap in and possible swap out. Right? So this I might update in the later if there's something important in it, but the actual thing is just like this. The idea is this, and it just like, gets simplified to this, right? So you have to access memory anyways, and because of that, you might, there's a rate of error which adds extra work for you. Alright? Does that kind of like says it? So, let's see. So an example, and just remember for all these, like nanosecond is 1,000 times less than microsecond, microsecond is 1,000 times less than millisecond. So a memory access time, we consider it like, 1 microsecond. And 50% of the time the page that is being replaced has been modified and therefore needs to be swapped out. This is talking about being the dirty rate of the pages, right? So swap page time is 10 milliseconds, which is 10,000 microseconds. Always convert all of them to 1. Like either, bring the millisecond to microsecond, bring a nanosecond to microsecond. Just like work with 1. And this is, in this question, we are assuming swap out and swap in time are equal, which is usually not the case. Swap out is usually takes longer because you want to write to the hard disk. Swap in is reading from the hard disk. But in this question, it's like, we're taking it simple. Whether you want to swap out or you want to swap in, that takes this much time. Now, it says like, what is the effective access time based on the page fault ratio? Alright. So, wake up and let's do this. I see some of you're dozing off. So, it's expected. Alright. So remember, the effective time is hit rate multiplied hit time, miss rate by miss time. So here, the hit rate we don't know. It is asking based on the page fault ratio. So 1 minus p m. This is the exact like this one, right? So the memory access time plus the page fault ratio and the cost for page fault. So a page fault, remember, it always includes a page in. You have to swap in a page when you need, the page. So that's the 10,000. However, you might need to swap out. What is the average swap out time? The ratio of dirty bits multiplied by the cost. So in this case, we said that the cost for swapping out is the same 10,000 microseconds. And we have the 50% of the time. So 50% of the time that you want to swap in, you also have to swap out. That adds this much extra. So then you just like add them up. The memory access time has been told is like 1 microsecond. And this one is, 15,000 by P. So this is the effective access time. So now the question asks, if every, out of every 1,000 references, one of them, is a page fault, what would be the actual, what would be the result? So you just have this, you basically take 1 out of 1,000 into P, multiply it, and then the effective access time is 16 microseconds. So this just gives you an idea. If the page fault ratio is 1 out of 1,000, you are degrading by 1,500%. Because normally, your physical hardware is allowing you to access 1 microsecond, but effectively, it takes you 16 microsecond on average.
Only replacing P with 1 over 1,000?
Yeah, this only we replace P with 1 out of 1,000. Okay? So this is horrible, right? I mean, compared to 1 microsecond. And now it asks you, so what is a paging demand paging algorithm that is good enough that ends up with only a 30% performance degradation? So if you are you are already at 100%, right? So if you have 30% degradation, that means your time, effective time, should be 130%, right? If you're 100, you degrade by 30%, that means the effective access time should be 130%, right? So you just like do that. So you say the effective access time, the goal effective access time divided by 1, which is right now, should be less than 130%. This is what we want. So if the effective access time, for example, is 1, obviously it's impossible, but that's going to be just like 100%. If it's 2, then that's 200%, right? So we want 130%, so we just like start with this. The effective access time, we have it already here. So 1 plus this is less than or equal 1.3. That's the 130%. And then basically you subtract 1 from both sides, and you get this, and you just like bring this to the other side. So the page fault ratio for a good algorithm that results in a less than 30% degradation should be less than like 2 out of each 100,000. I mean, I don't know what, like if you want to compare it to a percent, you just multiply by 100, that would be like 0.002 of a percent. Yes?
Doesn't that also depend on like the speed of like how fast you can actually access it, or like how fast?
That's the memory access time.
Is it always that?
No. And also, we're actually going to see in the next example. That itself is, if you remember, we have the TLB. That's not fixed. Based on your caching, this itself can be an average. Okay, so this example sums it up a little bit better. So this covers everything, both paging and like the TLB and the demand paging. So we say, okay, consider a paging system with the page table stored in memory. If a memory reference takes 200 nanoseconds, so this is, for example, it can be different. How long does a page memory reference take? So if a memory reference takes 200 nanoseconds, how long does a paged memory reference take? So it's already paged, so we already need to access it once, right? So we need to access to 400 nanosecond. So this example, sorry, I thought that we were past example 1. Exercise 1, we don't have TLB. So the page table is stored in memory, there's no TLB. Okay? So if each physical memory access time is like 200 nanosecond, we want to read the page table once, so we like spend 200 nanosecond there. When we get the frame, we actually access the physical memory, that's another 200 nanosecond, so that's it. 400 nanosecond. Now it asks, if we add and associate registers and 75% of all the page table references are found in the cache. So that means for each page reference, we don't have to access the page table in memory. 75% of the time it's already in the cache, which we consider to be 0 time. 25% of the time we need to access the page in the memory. So that's going to be calculated like this. Again, 75% of the time we read the TLB 0 time and then just like access memory once, which is 200 nanoseconds. For 25% of the time, the reference page is not in the TLB. We have to access the page table in memory, just like this. We need 400 nanoseconds. So then the total, you just like, count up. Okay? So this effective access time, what is it? What is the effective access time? What does it indicate this? Does it have to do with demand paging or virtual memory or just memory access? Do you have an idea? Okay. So you have to go with these exercises, and obviously if there's any question, post it later, but we want to cover it in class. But so this is just the effective access time of memory access itself. We didn't talk anything about virtual memory swapping out dirty or anything. The fact that we just want to address a page in memory, if it's like in TLB or not, will have a degradation from 200 nanosecond itself effectively to 250. Okay. Now, next part of this exercise, we'll add, this exercise, now basically add a level of more calculation. So you have to have like an effective access time of memory, but also virtual memory. So here it says, we have considering a demand paging system. That's the keyword usually because that, it says that, we have the virtual memory. where 40% of the page table is stored in registers, and that means 40% of the time that you want to access any memory, it is, you don't have to reference to the page table, versus 60% of it, you have to actually access that memory location twice. Anyways, assume any reference to the memory takes 100 nanoseconds. That's a physical limitation. And 20% of the time, the page that is being replaced has its dirty bit set to 1. Now we're talking about the virtual memory, right? So 80% of the time, you might have a page fault ratio. The page fault ratio is any time that the page fault is happening. 20% of the time, you have to swap out. 80% of the time, you only need to swap in. Okay. Now, this time it's giving you a different time. So swapping a page in takes 1 millisecond. Swapping a page out takes 2 milliseconds. This is a little bit more realistic, right? Now, you have to, pay attention how to use all these information, right? So how long does a page memory reference take? This itself is like, okay, if we don't have a page fault, what is the effective time of accessing memory, right? If it's already paged. So this is like the previous exercise. So 40% of the time, it is in the cache. 60% of the time, we have to access the memory twice, right? So the hit ratio and miss ratio. So we are using microsecond because we are, using between nanosecond and microsecond, milliseconds. So we pick the middle one. So everything is in microsecond. The hit rate is like 40% of the time. It's in the TLB. We only access memory once. 60% of the time, we have to access memory twice. Once for page table, once for the page. And so the effective access time is 1.6 of the memory, and that's like 160 nanosecond. Or if you want to turn everything to microsecond, that's 0.16. That's just like, like last example, calculating the effective memory access time. You can also, instead of hit rate and miss rate, calculate it a different way. I told you that I'm giving you 2 ways to calculate. You can say, okay, I always have to access memory once, right? Whether it's in the TLB or not, I have to access it. So I'm just going to keep it there. Sometimes I need to do some more work, which is for 60% of the time which the page is not stored in the registers, I have to access the memory one more time. And then this basically gives you the same number. It's just a different approach. Whatever you're comfortable with. Yes? There was a question. Yeah. Why is what? 2M. Because for each miss, that's a cache miss. So you want to refer to a page, but you don't know where that page is in the physical memory. So you need to look at the page table, right? So if it's a miss, that means the page table is not in your TLB, in the translation look aside buffer. You have to access the memory to look for the page table itself. And then read where that page is. And then access that page, like that frame, in the physical memory. Okay? So this is what's part one. Now consider this as the effective access time to memory instead of like a physical limitation of 100 nanoseconds. On average, you take 160 nanoseconds. So now we're talking about the demand paging. What is the EAT if the page fault? That was an if. If the page fault is 1 over 1,000. So this is now talking about demand paging and swapping out and swapping in, right? So what we need to do is, okay, again, the same 2 approaches, right? Hit rate and hit time, miss rate and miss time. And basically what we're going to do is we say, okay, so the page fault ratio is 1 over 1,000. That means 999 time out of 1,000. We're just going to do whatever that we were doing. But for 1,000th of a time, we need to swap out and swap in. We do extra work, right? So 1 minus P, average hit rate, which is just what we just calculated in the last page, but it's just going to be 1 minus P. For the P, the average miss rate is going to be the same memory access time. Also swapping in, which takes 1,000 microseconds. Also an average swapping out, which is 20% of the time, which is dirty, we have to swap out. Okay? So then you just like do some, math. It might be usually simple, but you just don't make any mistake. In this example, again, these usually this will cancel out with this, and you should like ignore, don't add 1,000 with this number, for example. We don't want them, right? We just like want the rounded numbers. So this is basically gives you the memory access time and the 1400p, which is in term like 1.56 microseconds. Okay. The second approach, which is again my preference, is easier. Again, I'm more comfortable with it. I say that, okay, I have to access memory anyways, whether it is the page fault or not. Okay, but if it is a page fault, I need to do some extra work. That's just overhead. So I calculated it this way. So I'm saying, okay, memory access time we just calculated. On average, it takes 160 nanoseconds. And the extra overhead is for when we have a page fault. So the page fault ratio is 40%. And, the page fault ratio is 1 over 1,000. And whenever the page fault is happening, I, again, need to swap in anyways. And I might need to swap out. So I'm just calculating those separately. In this parenthesis, the swap page, which is always there, is 1,000. 20% of the time, I'm also swapping out, right? So that's the time for swap out. That's the ratio for swap out. That is always swapping in. You just add them up. You multiply by p. You get the same result. Okay. However you feel more comfortable to calculate it, it's just like up to you. But basically, these are the two approaches and ideas. Okay. Any question? Let's move on. All right. Next idea is thrashing. This is also important. It might show up, in your exam, for example, as a question, because the idea is important. Thrashing is when you don't have when a process is like doesn't have any free page in memory. It wants to swap out, right? And then maybe it wants that page again, so it has to swap in and swap out another page. And then maybe it wants that page again, so it's now swapping in and swap out. So like the CPU is just doing the juggling pages instead of actually doing useful work, right? That's called thrashing. So when the computer's virtual memory is like overused, so basically, if you remember, the idea of virtual memory was for when we increase the level of multi-programming, so that each process has their own, the pages that they need at a time, and then they refer to those pages and then work, right? But if we overuse it, if we have like too many processes, or each process, one of them processes, whatever, they need to access a lot of pages quickly, right? Then the CPU is just like, has to like deal with a lot of swapping in and out instead of doing useful work. Now the problem gets worse because when this happens, the CPU is like waiting for the hard drive, right? Swap out, swap in. The CPU won't be as busy. It's just like waiting for the hard drive to do this, right? So when you look at the utilization of the utilization of CPU actually becomes lower. Because CPU is just like waiting for the disk always, right? It's just waiting for a page until it can do something. It runs a couple of instructions, for example, and then again it has to like wait for another page. So when this happens, the operating system might just get tricked. It looks at the utilization of the CPU and realizes that, CPU is not utilized enough. CPU can do more work. So let's add another process, right? And that makes it worse because that process itself needs memory. And now that will lead into less available memory and more thrashing, right? So thrashing is actually when this happens. So let's take a look at the graph in this. So the degree of multi-programming and the CPU utilization has something like this. So when you start, CPU is only one program. It's obviously doing I/O or whatever. The CPU is not going to be busy all the time. As you increase the number of processes, then the CPU can juggle more processes at the same time and basically use the memory, better. But at some point, you start overutilizing the virtual memory, and then what happens is that now the CPU cannot work because the pages are not available for the processes, and as you increase the degree of multiprogramming, this only gets worse, and then your system can, crash. Okay? So this is called crashing. So, and then you have to be able to detect if the system is thrashing or the system can take. So, what is the solution to thrashing? What is the solution to thrashing? Huh? Go ahead. Yes. Reset that, okay, like be a little bit more lenient. That's a little bit harsh. Reset, instead of like resetting the whole system, what you can do is, yes? Remove some of the processes, because this was caused because of like the programs, right? If you reduce a couple of those, pause them, remove them, whatever, then you will have like more available because, they were taking so much of resources, right? So, consider a demand paging computer where the degree of multiprogramming is currently fixed at 4. That number doesn't matter here. The system was recently measured to determine utilization of CPU and the paging disk. Now the results are one of the following alternatives. We have like A, B, and C. And for each case, what is happening, and can you increase the degree of multiprogramming to increase the CPU utilization? Okay, this is what the operating system to be able to decide. So if the operating system looks at the system and then realizes that the CPU utilization is 96% and the disk utilization is 4%, what is happening to the system? Go on. Yes. Okay, thrashing. Why? Okay, but as we just realized, when thrashing happens, the CPU is not actually being utilized. It's waiting for the I/O, for the disk. So this is not thrashing. What's happening here now? Yes. Okay, here we are not looking at the memory. We don't know the use of memory. We are looking at the disk, which is the swap or page fault rate. So here we don't have any idea about how that process is utilizing memory, but we only see that, okay, the CPU utilization is sufficiently high, right? The CPU is utilizing, and it is not thrashing because it's not like, using a lot of disk. So it's just like doing work, either like CPU intensive or memory intensive. We don't know, but it's like fine. And, we don't need to do anything. Increasing the degree of multiprogramming only will, degrade the CPU utilization, right? So this is actually a good situation for, CPU. Next, if we take a look and then we realize the CPU utilization is 10% and then disk utilization is 95%. So what's going on? Now it's thrashing. CPU is just waiting for the disk all the time, okay? So here, we cannot increase the CPU utilization by adding anything more into the memory. Okay? This is the example. Now, it also could, by the way, be a situation that one of the processes is keeping the disk busy, for example, if they're copying files from here to here. That can also increase the, disk utilization. But in that case, you won't see this. I think that way actually they can utilize the MMU. So, that the operating system will probably know anyways. So, next would be CPU utilization is 12% and disk utilization is 2%. So what's going on? Maybe somewhere from here. If we take a look at the system, CPU is utilizing like 12% and disk is also 2%. What's going on? Yes. Okay. So, can we increase the degree of multiprogramming? Sure, why not? Right? The CPU is underutilized and the disk utilization is not low. That means that the CPU is not underutilized because of paging, swapping in and out to the disk. So it's either, we don't have many processes or they're waiting for other IOs, which we can basically add other processes, right? So that's, the idea. So another question is this one. Consider demand paging system with the following time measure. The CPU utilization is 18%, paging disk is 96%, and other I/O devices is 6%. Okay? So what does that show to you at the first sight? Huh? It's thrashing. It seems like it's thrashing, right? The CPU is not utilized, but the page disk is, right? For each of the following, say whether it will or is likely to improve CPU utilization. Answer with yes or no, likely, and justify the answers, right? Again, these are important because you have to grasp the concept to have an idea on this, right? So we can tell that it's probably thrashing. So does it help if we install a faster CPU? No, why not? Exactly. Right now the problem is not CPU. It's like something else, right? The CPU will be actually more bored, right? So the utilization will come even less for the CPU, right? So, does it help if we install a bigger paging disk? Paging disk refers to the storage. Likely. Why? So the bottleneck is not the limitation of the capacity of the storage, it's the speed of communication to the storage. It's the write and read speed. So if you increase the capacity of the storage, it probably doesn't help. And we are here talking about a normal disk. So if it's like an SSD, that's different because it might do some parallel whatever, right? But a normal disk, it doesn't help. You might have 1 terabyte of free memory. The bus is still SATA, 300 gigabit per second, whatever it is, right? So that's the limitation. So the next one, decrease the degree of multiprogramming. Is that going to help or not? Yeah, because it's thrashing, so decreasing the multiprogramming, it will actually let us have more available memory for the other processes, and then that will lead to save us from the thrashing. Okay. The next one is install more main memory. Is that going to help or not? Yes. The answer is likely because more pages can remain resident and do not require paging. But this also depends on the algorithm that if your paging algorithm can utilize your frames better. So it's likely yes or yes.
It depends on how much more we install.
How much more?
Install enough to cover all of the processes.
Yes. Yes, if you install enough memory technically that you would not need paging, that doesn't happen. But for example, actually this is something sometimes I suffer in my office, that Linux has a swappiness, and it's one of the kernel parameters, it's called swappiness. A lot of the time swapping does not happen only when you are full in memory. So a lot of the time you actually see that the Linux is swapping, but you have available memory. It's just slow. So I don't know why exactly, what's the algorithm behind it, but sometimes I feel it's stupid, right? So fortunately, it will allow you with administrator access to reduce that level of swappiness, and because exactly that's the case. So I have a lot of memory, physical memory, but I don't know why it wants to keep half of it free. So it, keeps, doing paging, which, I don't like. So, but technically, again, if you have the, not a stupid algorithm, then it can actually utilize that memory, and it is yes. All right? Any question in any of these examples? All right. So for next session, make sure you, the due date for design doc is this Friday, and argument passing is also, you have to finish it up and go on with the syscall handler. And homework assignment is also on next Thursday. You are done with homework 3 concepts or topics. So you can actually solve it. If you have an issue or question from them, you can start posting them on Piazza. All right?